Our next speaker is Pau Colomer, and he's going to present their recent workaround for the simultaneous smoothing problem.
Thank you very much. So I'm going to talk about this project. We recently published the archive with this monstrous 910 screen. Just by scanning this QR, you can go to the article if you want to follow it or later the presentation. And I want to thank not only the organizers but also my supervisor and yes, Winter for his patience and his amazing ideas. So thank you. Okay, so let's start by breaking down this monstrous title in different bits so that we can see understand the outline of this presentation. I will start talking about the problem at hand, and I will explain why we want to cheat it with total unitaries and without simultaneous smoothing. Then I will present the results and finally some examples of applications to multi-user information, multi-user information. So let's start with the problem at hand, which is the coupling. In the coupling, we have this initial state which is correlated between the systems A and E, and we want to do some local manipulations on the first system on A, such that the output is something uncorrelated from if and also uniform. So that's the main idea, and this problem was tackled mathematically before. What we want to do is this thing here. So we want to see that the expectation value of the trace distance between this manipulation and the ideal data coupling, let's say, is something small, meaning that we have achieved, let's say, the coupling. So this problem was tackled by some people in this room, we, Mario Beta, Wuchler, and and they found out that with the process that consists of a random unitary chosen from a space-time followed by CBTP map, we can actually run this mathematical thing in the bottom of your screens as this expression we can see here. And notice that we have this term accounting for the initial correlation of the map, and also another term accounting for the, let's say, the decoupling power of the map, which is something that we would expect in the video, right? This is quite intuitive, and we also have this term accounting for the smoothing of the mean entropy. So what we want to do now is transform this setting into a multiple type version, and this means we will have many aliases, say 1, 2, 8, and we will write on each one of them this random unitary locally, and finally a global fixed CPP map, such that the, let's say, the overall the final outcome is the thing we can see on the screen. It looks messy, but it's just the generalization of the thing before, so something uncorrelated from it and uniform. So that's the main idea. Mathematically, again, it looks messy, but it's the same as before. We have the unitaries followed by the CPP map, and we want this to be, the expected value of the trace distance to be similar to this ideal the state that we see on the right hand side. So that's the main idea. We want to do this, and the problem, well, what we would expect now is similar as before. We would expect to have some terms accounting for the correlations between each of the aliases and if, and also to have terms accounting for each of the aliases and the coupling power for each of these local, let's say, application of the map. But we would also expect to have some terms accounting for, let's say, alias 1 and alias 2 and if, so the correlation between the first two aliases and if. So we expect these many terms which can be expressed like this here, where this uppercase I means we are a partition, a subsystem of this aliases system. And the problem we see now is that when we try to smooth, and before we had these smooth mean entropies for the term accounting for the correlation of the initial state. And now if we want to do this kind of more general thing, we can find that we need simultaneous smoothing to smooth this term here. Let me explain and tell you something about the smoothing so that everyone is the same page, despite that this has been discussed in other talks. Smoothing consists on using optimizing entropy, using the best state in epsilon ball around our input state. So that's an idea. Simultaneous smoothing, on the other hand, means that by modifying, let's say, the global input state, we expect that each of the marginals of this input state appear smooth, like automatically. This is simultaneous smoothing conjecture, and has been out there for like 20 years and has never been proved. So we would like to Yeah, so let's to state our theorems without having to use this conjecture. Maybe one example so that this can be understood further. If you want to optimize, imagine these two entropies you can see on the screen. Simultaneous moving would mean that we find this rho prime, this state rho prime, that optimizes the whole, let's say, the general entropy accounting for A, B, and C, let's say, and this rho prime, like automatically, would optimize also the marginals of the entropy of the marginal state. This we don't know that it can be done, so we want to do independent smoothing, which is that in the back. So optimizing independently each one of these different entropys. That's the idea. So how can we do this? And this is the main trick that we use to avoid simultaneous smoothing. It may not be super trivial to see this directly, but notice that this expectation value of this trace distance will always refer on the same, let's say I have this again, the same input state, which is this one here, and this in turn, after all the mathematical manipulations, will result in simultaneous smoothing. Let me just keep going. Maybe this is not so clear right now, but in a minute it will be more clear when you see like the thing, the substitution that the thing we use to avoid simultaneous smoothing. So the trick is first to find these maps. The first one is just a difference between the application of the random imagery and the polarizing channel. And the second one is just the map that applies correctly the global, let's say, CDP map on the partial system that only accounts for, let's say, I axis, so only for a partition of the axis. This is the main idea. And the thing we do now is the stereoscopic trick, which is just the application of the distributed flow, right? Notice that because of this minus sign that you have here, when we expand this zone here, we'll have many terms, and most of them, like, magically, will cancel out. So this thing here is exactly the same as this thing here. And now, just like well, you can check this on the like in the two Alice's case, and it's pretty simple to see that it will scale correctly for many axes. So the thing now is to apply the definition of this map here, and finally the triangular inequality, and we find that this thing, this expectation value, this expectation value here, can be upper bounded by this other smaller one here. And now if we compare these two expectation value, we can see that indeed, when we manipulate this thing here, we will find in the end of all our manipulations, we will only have to smooth terms accounting for each of the marginals of the input state instead of having to optimize them all over the same input state. So this is the trick that allows us to skip simultaneous. That's the main idea, and I have to say that it was parallelly used by Mario on how to change in this other aspect you can check here on this thing. They use it for the broadcast channel. Well, yeah, but the main trick is exactly the same. The telescopic trick is exactly the same. So all the way to them too. Yeah, so let's keep going on and find the main result of this thing. This is the value we want to find, and as we have seen, the first thing we need is the sum over all these different partition of the aliases, which will be all the terms that we need. And we did find, similarly to the old paper in decoupling, like the restricted decoupling, we find this term, the contemplation, initial correlation of the channel and the decoupling power of the state and the decoupling power of the channel. We also find a term that relates to this smoothing parameter, and finally this constant before the exponential, which is the one that we're going to use. So this is our main theorem, and now intuitively, if you're not used to this full notation, you can understand this by looking at these entropys, and notice that if we have stronger correlations on our input state, this entropy will be smaller. This is a negative exponent, so the bound will be in general greater, and this will result in a poorer decoupling because this is a greater bound, and it means more difference between our manipulation and the idea of the pattern. Similarly, if our map is very closer to the entity, so doing nothing, the entities will be smaller, so again we will have worse decoupling. This is the main idea. And the way to see to understand this all these entities individually. Now let me just focus for a moment in this constant here, which is missing here, because we found a corollary that when we use a map that has this structure, so a map that can be applied locally, this is a expression from the more general kind of map that we can apply, we find that actually this constant can be made much smaller, and this is very nice because, as we have seen, the smaller bound is better becoming, but also because these kind of maps are the ones that are most used in the applications, so it's nice to have this result. These are all the results I wanted to present. Now let's just try to apply those to some quantum information tasks. The first one and the most direct one, okay, that I said already, is a local randomness extraction, which consists of convert weak randomness contained on this input state into uniform randomness. This is the main idea, and notice now that just by defining this fixity map to be a local quantum classical channel, as we know how this channel applies to the identity, we can write this thing just as this one, as this expression here, which is exactly what we want to achieve. These are random bits, uniform random bits, uncorrelated from any site information we might have, or if we might have, right? So this is exactly what we want to do. So just by direct application of our theorem, this is exactly what we had before. This is the application of our theorem. We have this first bound, and now what we want to see is that we can make this bound, or better, under which conditions we can make this bound arbitrarily small, meaning that we have achieved with arbitrary precision, let's say this amount, certain amount of randomness. So now, as we know, the expression, well, how to calculate this expression for the quantum channel, this in here, we can just see that if we define this term here to have, this expression you can see here, we combine this whole thing to be, to be proportional to epsilon, and therefore to be as small as we want. And this thing here, sorry for the change of notation, this Ti is the amount of random bits that we can extract from the process. It's similar to this size of the output state. This is telling us the maximum amount of random bits that we can extract from our input channel. So with this process and given this channel, we can extract, calculating this thing, this amount of random bits. Notice that this bound is trivial if this term is positive, because the logarithm of the input space is always bigger than the logarithm of the output space. But as this thing could be small, we might as well substitute this term for the negative part of this term. Okay, so these now are the one-shot, the cheatable one-shot codes for local randomness extraction. Now, just by direct application of the asymptotic deportation theorem, we can change this smooth mean entropy by Newman, condition of a Newman entropy, the negative part again, and we find the asymptotic IID rate for many copies of our input state. So these are the results for local randomness extraction. Let me just give some information for this again for the table measures to this notation. First, for a larger input state, it is obvious that we will have more extractable random bits. This is very intuitive. And again, if we have stronger correlations on our input channel, this will result in smaller entities and therefore less extractable random bits, which is again very intuitive, because if the input state is more correlated, it makes sense that it will be more difficult to break it down into uncorrelated and to get this randomness, this uniform randomness. So that's local randomness extraction, which is, as I said, the most easy application of the theory. This is maybe a more difficult one, which is multipartite entanglement resistance, which consists of even a pure state. We want to output doing some local operations and classical communications. We want to get this maximum mixed state of Schmidt-Brandt. Here we are interested on this Schmidt-Brandt. Which Schmidt-Brandt can we obtain given a certain input state? And we do this procedure again here. We will start with a random unitary as always, and after that we will apply a projective measurement on A and some destructive measurement on this calipers denoted by C. We will store the outputs that each of these measurements give us, and then we will prove, I will tell you in a minute, how that by broadcasting classically these outputs we can define these unitaries that allow us to finally get the maximum amount of the state. So the idea here is a bit different as the one before. The thing is that the principles of information theory, if we have a pure state and the imaginary of this pure state is maximally mixed, then this initial pure state has to be maximally entangled. And this is the thing that we use, because notice that now, if we find here in this part here a maximally mixed state, we will be proving that the whole thing, as we is maintaining the purity, the whole thing is maximally entangled. So that's the idea here. And by using our theorem, we can find how the conditions under which we can find this identity here, which are these ones you can see in the screen. Again, notice that this is telling us the maximum amount of what the maximum number of shoot rank that we can get with a given initially with the state. And these are the one-shot rates. And the second expression here, okay, the laser just died, so I'm just want to point. The second expression here is just telling us that that if we have some pure marginals in these helpers, we just have to discard them because they will mess up our protocol. So if we have, for some reason, some of the helpers are in a pure state, we can just discard those so that our protocol functions correctly. Again, we just apply the symptotic condition theorem to get the IID limit, so the limit of n going to infinity rate for multi-particle entanglement assistance. Let me do another application. Okay, the whole thing, like, not only the laser. So, okay. This next one is state merging, which consists on sending a share of a state from Alice to Bob, and Bob already has, let's say, some part of this state. This is triggered if we have a quantum channel, because we just send your share to a quantum channel, but we want to do this with local operations and classical communication, and we use some extra entanglement as a resource so that this process can be done. After we send the local operations and classical communications is share of a state, we will be left with some entanglement, and very interested on this difference between entanglement that we have at the beginning and the one that we have in the end, so the amount of entanglement that we use for this process. In a more general setting, this was like only a background scenario for state merging. We have this big state, let's say, shared by all the Alices A1 to A3 and Bob, and also reference systems that will maintain our purity. And also we have some entanglement between each of the Alices and Bob. Now we apply quantum instrument to each of the Alices, and we get this output system. And the application of our theorem is very similar as the case before. The thing is that if we find something that is maximally mixed here, as this state will be pure because this maintaining the purity here, we will find that we get these maximally entangled state in the end. And we can find with our theorem the conditions under which this can be done, which is the one you can see outside. The thing now is that we can prove that by broadcasting classically the results of each of these quantum instruments, and with this condition of the maximum mixed stage on the Alice system, we can define the voting function that will end up giving us in the end this leftover entanglement between all the Alices and Bob, and the input system, something that is similar, close to this initial pure system that we have. But now all this system is carried by Bob. Notice that by defining these one-shot rates as a difference, as I told you before, we can simplify this expression above by this here. And we could also, again, use the asymptotic equipartition theorem to change this smooth maximum dimension to continuum dimension. So these are the one-shot, and it would be the IID asymptotic moment rates. Finally, just the last one, I'm sorry, I'm rushing a lot. Quantum communication through quantum multiple access channel. Here we have some states, so rho 1 to rho k, that Alice have and wants to send to a single Bob, see? And she will use some encoding function, and after that, she will send these states to a multiple access channel, and the channel outputs something that will be encoded by Bob, and Bob wants to obtain this rho hat and to rho k hat, which are like similar states to the ones that Alice wanted to send. This is the main idea, and I think it's how can we apply our theorem. Notice that here, sorry, we are interested in the maximum size of these rho 1 to rho k messages that we can send. And now, again, notice that the most difficult thing that we can send to a quantum multi-channel entanglement. So we can substitute this protocol through this thing here. So just sending a share of a maximum entangled stage of an ED, and if we achieve that in the end, after all the communication is encoding in channel and misdecoding, we can again have a maximum entangled state. We would have proven that we can send any message, because if you can send entanglement, you can send anything. So the thing now is how can we use our theorem here? This is a bit more intricate, and I'm not gonna be super specific about it, because we have to use this state you see at top, which is a state it's not the things as before where we had the initial state that we manipulated it. This is like a state that we use for the proof that considers not only input state but the application of the channel itself. This B is the isometry from an extensive dilation. So, well, yeah, we have to use our theorem over this input state, which is a bit more interesting. The thing is that the marginal summate of this input state, we can prove that after some unitary follower like the CBT demand, which is the way to apply our theorem, we can find something that is again uniformly correlated, and from this, like very similarly to the cases before, we can prove that there exists this maximally global entangled state between the two parties. This is the main idea. I'm sorry, I cannot get much into it. And we find that this is fulfilled. We can find this maximum mixed state if, and therefore the maximum entangled state at the end of the protocol, if this condition is fulfilled. And notice that again, this is a bound on the maximum size of the states that we can send to is the thing that yeah, so we conclude that there is a good code for quantum communication through a quantum multiple access channel if this condition is fulfilled. And now again, this is like applying one more time the study prediction theorem. We can find the IID for having many input states that which is this one. These are all the results I wanted to comment. Just to finish in a minute, let me show you this table, which compares the previous state of the art before this project and the new results that we have found. Some of them were already out there, were already known, and we have only reproduced it. We have to say with a simple protocol that the one that was used. Other ones were conjecture, and we proved that they existed, and some of them, like the ones that were used for multi-party controlling of the system, just didn't exist, and we actually have it. So these are all the results that come out from this beautiful project, and yeah, and that's everything I wanted to say. Thank you. Hello.
Can you explain once more the trade-off between local and global channels?
Sorry, between?
You said that when you instead of the global map, you use local maps, and some constant improves. But like there must be some kind of trade-off with the entropy.
A trade-off between
that constant and the entropies that you get from the channel. Or can you just explain?
The entropies are just like, well, I have to go a lot, but maybe I will do quicker. I just escape this. Okay, I understand things. Hello. Okay, it didn't work. Now, yeah, so the thing here is that we previously had this constant here, which is a pretty big thing. And the thing is that in the condition, if this map is applied not globally like this one here, but locally on each of the alices, so this is this global map has some vectorial structure on A1 to AK, we can actually provide mathematically. It's actually a funny story because it came out from an error I made, and we found that we got a better map. So this is how we found this result. But yeah, this is exactly just by applying this CPTP maps locally, this constantly for this exponential of the interest in terms, let's say, is much smaller. But all the other terms are exactly the same. So you would just have this thing here, this same expression here, but it only changes this constant.
Okay, so why would I then use the goal map to use constant?
Well, I mean, we just present it for more generality. Okay. I mean, if you could, we don't actually have any application where you use like the global map instead of local ones, but maybe there is one. I don't know. Maybe there is can have some brilliant idea on that. But yeah, I don't have any idea why would you use a global map, but we use that one for generality issues. And this is the more general setting that you could find maybe some application of this. I mean, in the end, having this tensorial structure is just a restriction of this input channel that you're sorry, the channel you're using. So,
but it seems operationally more relevant.
Yeah. As I said, all the applications are we actually use this protocol.
Maybe one more.
So in this main code, your input condition is not smooth. Is there a way to smooth necessary?
So you mean the second entropy is not smooth? Yeah, well, you can smooth that one also. I mean, it's a decision you can make. The smooth mean entropy is an upper bound of this thing here, so a lower bound of this thing here. So you can always do that. But we decided to keep these collision entropes for. I mean, sorry, I can hear you.
So for smoothing this entropy quantity, you perturb your super operator. So would they create a tussle with the first step?
No, I mean, it's a different thing, right? On the input state, yeah, I don't think you would affect that. Well, why would it affect the smoothing of the channel? Of these steps. So
that was what was shown in the vanilla interpretation. That in order to smooth both the entities, you have to perturb your super operator. That's how
yeah. I'm not sure about that. Let's discuss it later because I don't think I'm understanding the question completely. Well, thank you.
Okay, then I think let's thank the speaker again.